Well, just to round things out, you also mentioned quantum tunneling earlier, and
Hmm.
quantum tunneling in close to 200 episodes has never come up on the show, and there have been a lot of episodes on quantum mechanics. So, just what is quantum tunneling, and then where does it fit into certain enzymatic reactions?
Yeah, so quantum tunneling is a feature of the quantum world that we've known since almost the beginning of the birth of quantum mechanics. It's the way we explain radioactive decay. A particle, say radium or something, that's a nucleus that is radioactive that spits out an alpha particle. That alpha particle shouldn't be able to escape the nucleus. What it has to do is punch through an energy barrier, what's called the Coulomb barrier. Um, we now know that quantum tunneling, is everywhere. It's the reason why the sun shines, because two hydrogen atoms, or two nuclei of hydrogen atoms, two protons, shouldn't in just described in classical mechanics without any quantumness, should not be able to get close enough together to stick in the first step towards thermonuclear fusion, which is what gives the sun its light and heat. Because two protons are positively charged electrically, so they repel. So there's a barrier that stops them from getting too close. But because in the quantum world, these things aren't really discrete particles, they are spread out waves.
Mm-hmm.
They can leak through these energy barriers. I always talk about it it's like a ghost or phantom passing through a solid wall. There's a certain probability that these two protons can, or think of one staying where it is and the other getting through the energy barrier. Once they get close enough, then the strong nuclear force, which is an attractive force at very close distances, kicks in and they bind, and then you get the process of hydrogen, the first step of hydrogen becoming helium in fusion. But it's a strange effect. It's a bit like kicking a soccer ball up a hill. You got to give it a big enough kick to get it over the hump of the hill. In the quantum world, you could kick it halfway up and it still has a non-zero chance of disappearing on one side and just reappearing on the other. It has quantum tunneled through a region where, were it a classical particle, it would not be allowed to pass through. So we see this all the time in physics and chemistry. It's not a surprise. What was a surprise was to find it taking place inside living cells. The first people to see quantum tunneling was quantum tunneling of electrons in spectroscopy in the 1960s. Then in the 1980s, a group at Berkeley in California saw quantum tunneling of protons, 2,000 times the mass of an electron. So clearly much more difficult, a heavier particle, but nevertheless quantum tunneling from one part of a molecule to another. And they showed that enzymes make use of this trick in moving particles around. Enzymes essentially are the workhorses of the cell. They break and build other particles, proteins inside the cell. And one of their tricks is to shuffle and move particles around, and they use quantum tunneling to do this part of the time. So that was established in the 1980s. So it's not like a very recent thing. What we're interested in is quantum tunneling in a different mechanism, namely in the hydrogen bonds that hold the strands of DNA together. That's what the new area is that we're looking at.
Hmm. And so then, in both of these cases, with the robin and the DNA, the idea is that entanglement and tunneling are fundamental features of the world happening all over the place. And then, as you said earlier, it's only natural that through natural selection, evolution would take advantage of these features for reproductive success.
Yeah, but by taking advantage of life would have had to evolve the ability for this behavior to take place in cells in a way that it wouldn't normally take place in inanimate matter with that temperature, with that complexity. I mean, the DNA example is that you've got these the double helix, the strands of DNA is like a twisted ladder. The rungs of the
Right.
ladder are hydrogen bonds. Those are, as far as I'm concerned, those are protons. I don't talk about hydrogen atoms because my background is nuclear physics, so I don't care about the electrons. I leave them for the chemists. I deal with the nucleus of hydrogen, the proton. So this proton can quantum tunnel across from one side to the other. We've published several papers over the last few years, very sophisticated sort of computational chemistry simulations to show that this is very likely to happen. And if the proton quantum tunnels from one strand of DNA to the other, then when the DNA strands unzip in the process of replication, you unzip them and then each one has a copy made of the other one that it attaches to, and you get two double helices. If the proton's in the wrong place in any one of these sites between the two strands, that could lead to a mutation in that base. And so it's important, that life has life evolved the ability to see these quantum effects. The point is that quantum tunneling, quantum entanglement, long-lived quantum coherence is another example in photosynthesis where quantum biologists are interested, should all disappear very, very quickly. Decoherence should kill off any quantumness far more quickly than the processes of life can make use of. And what seems to be happening, this is what really interests me, is the structure of the environment surrounding this quantum system such that it can stave off decoherence, maintain quantum coherence for long enough for it to play a biological functional role. So, the structured environment is what's interesting. And if that is true, then hey, why not? Life has had billions of years, so it will, any tricks that might have been available to it, it would have finessed over generation after generation after generation. And so those cells where they've been able to